This session is about a method for solving linear equations called the method of integrating factors. Kind of a strange name, integrating factors. Why are they called integrating factors? Well, as you'll see, they're things that we multiply, so we'll call them factors, and we end up integrating them to, thus the name integrating factors. It applies to first order scalar differential equations of this form. If you watch the video on the method of undetermined coefficients examples, you'll see that we already considered in that video examples like this, and we used that method of undetermined coefficients to solve this kind of equation in certain special cases. The special case where that applied most nicely was where the a of t was a constant, quite often called lambda, and the b of t is a function we're pretty familiar with. Exponential function, trig function like a sine or a cosine, and if you look in the book you'll also see examples where b of t is a polynomial, hopefully a simple polynomial like t or t squared. In those kinds of situations you can use the method of undetermined coefficients to help you solve this kind of equation. Today we're going to consider another method called the method of integrating factors. Both methods have their pluses and their minuses. We'll see that the method of integrating factors, while again theoretically applying to all kinds of examples like this, well, in practice, it doesn't mean you can actually follow it through to its final conclusion and actually solve the equation explicitly in terms of functions that you're used to. Let's consider a special case, a special example. This is going to look kind of complicated. I'll make it dy dt equals t squared times a quantity in parentheses here, 1 minus y over 1 plus t cubed. Certainly kind of a frightening looking differential equation. How in the world are we going to solve this? Well, separation of variables is kind of the first thing to think about. Can we separate the t and the y on the right hand side? And if you look at this, it looks like we probably can't. You've got them kind of intertwined there and they could be separated, but well, you'd have to try to factor out the part involving t, and if you did that, then that one would end up involving t after you factor out the 1 over 1 plus t cubed from that one. Separation of variables is not going to work. Is this even in that form? It doesn't look like it. But appearances can be deceiving. If you distribute the t squared through the parentheses here and then do a little rearranging, you can make it look like this. Negative t squared over 1 plus t cubed y plus t squared. And if you look at that and compare, you see that there's a match. This function right here would be the a of t. This function over here would be the b of t. So it can be put in this form. It is a linear differential equation. It would be a hard equation to solve with the method of undetermined coefficients, which is sort of the next thing you probably would want to think about, mostly because that's not a constant. In that case, think about using integrating factors. Here's what you want to do. Write it so that the left-hand side is in what I've called differential operator form. In other words, bring the term that involves y at the right-hand side over to the left-hand side by, in this case, adding t squared over 1 plus t cubed times y to both sides of the equation. So that the equation looks like this. When it's in that form, when we use the method of integrating factors, it was useful because we imagine the left-hand side as being what's called a differential operator. Sort of like a function where you imagine plugging in functions in place of y as input and getting whatever you get out from that expression out as output. And your goal in finding a particular solution would be to have an output of t squared. It would be hard to make a guess for a particular solution here because, again, once again, that is not a constant function. If it were a constant function, guessing something involving a third-degree polynomial would be perhaps a good guess. But we want to use integrating factors, another method. We'll see that even though this is complicated, the method of integrating factors is going to help us in this case. Now, the method of integrating factors, like a lot of these techniques for solving differential equations, involves a little trick. It's a little trick that, well, over many, many years, people finally figured out after scratching their heads with such equations to try to solve them. And the trick is based on looking at this expression on the left-hand side and saying to yourself, you know, that's almost like what I would get out from a product rule. Remember the product rule for derivatives. If you've got the product of two functions and you want to differentiate it, you take the derivative of the first function, multiply times the second function, plus the first function times the derivative of the second function. We've got a dy dt there and a y there. It's almost like if you treat y of t, as the first function, so y of t playing the role of f here, it's like that's an f prime and that's an f there, and that would have to play the role of g prime if we're going to match the pattern here with this rule. This t squared over 1 plus t cubed would play the role of g prime. The only problem here is that we don't have a g right here. We don't have a function whose derivative is this thing. What kind of function would have a derivative equal to that? Well, I guess it would be a natural log of 1 plus t cubed, and I guess we'd have another factor of 1/3 in front. If only that were there, if only 1/3 natural log of 1 plus t cubed were right there, we'd be able to solve this equation because the left-hand side would be the derivative of the product of that natural log and y based on this product rule. Well, it's not there. It's tempting to maybe try to put it there, but if I put it there, I have to compensate by putting it everywhere else. A certain kind of trick ends up effectively doing what we need to do. Let me just show you the formula for the trick and work it through, and then we'll think about why it works. We create this thing called an integrating factor, which is traditionally labeled with the Greek letter mu. It's going to be a function, mu of t in this case. Turns out to equal e to a certain power. What power? The power is going to be a function of t. In fact, you can take the power to be any antiderivative of this function here that's in front of the y when you write it in this form. The textbook calls that function g of t. So here initially I'll call that function g of t. That we integrate right there. There's no clear reason, there should be no clear reason in your mind why this is going to work. But let's just work it out and see the magic of integrating factors at work. And you can see by doing that integral, I am going to get this natural log involved. I'll get 1/3 natural log of 1 plus t cubed. I don't need a plus c because I just want one antiderivative. And in fact, I don't have to bother putting absolute value signs either because I just want one antiderivative. This is good enough. In this particular example, it's sort of contrived in such a way that this is going to work out nicely. This is going to simplify by using properties of logarithms. I'm going to be able to take that 1/3 and put it in the power of the 1 plus t cubed, and then use the fact that e and natural log are inverse functions to write this function mu of t in the simplified form as 1 plus t cubed quantity to the 1/3 power, or in other words, the cube root of 1 plus t cubed. That's going to be my integrating factor. Now I said initially that it's a factor in the sense that it's going to be a part of a product. In fact, this function is what we're going to take and multiply both sides with. Let's do that here. See, multiplying both sides by that natural logarithm wouldn't really end up working because of the fact that I end up having to multiply it here too. But this is just the thing that we need. 1 plus t cubed to the 1/3 power to multiply everything in the differential equation by and use properties of exponents to get a differential equation that amazingly we can solve. And you'll see how in just a minute here. Looks probably more complicated, but it actually is going to be easier to solve. Just double check, compare it with the original equation. This is a plus sign here. I multiplied the 1 plus t cubed to the 1/3 power times that, times this, and I used property of exponents. I've got a 1 plus t cubed in the denominator. That's the same as 1 plus t cubed to the -1 power, so I took a 1/3 minus 1 to get the -2/3, and I also multiply it by t squared. So here's the magic. This thing on the left-hand side is actually what you would get if you differentiated the following product. The product of the integrating factor, mu of t, 1 plus t cubed to the 1/3 power, times the function that we want to solve for. That's what this left-hand side equals. Think about it. This is a product. Imagine using the product rule. That's my first function. There's my second. I've got the first function times the derivative of the second. I guess I'm doing it in the opposite order of what I had over there. Plus the second function, the y, times the derivative of the first. I claim this is the derivative of the first function. Imagine doing that in your head with the chain rule. Focus in on this thing right here. I would bring the 1/3 down in front, get a 1 plus t cubed to the -2/3 power. That looks good. And then from the chain rule, I get an extra factor of 3t squared. The 1/3 and the 3 would cancel, and I'd be left with just a product of t squared. So this really is what you're going to get out from the product rule. And now what you want to do is you want to integrate both sides. Integrate both sides of this equation. This left-hand side looks kind of ugly, but it's actually not. You've got an integral of a derivative of something. Integration and differentiation are inverse processes. This is going to simplify just to 1 plus t cubed to the 1/3 power times the unknown function y. It's like the integral and derivative cancel in a sense. Start with the function, differentiate it, get its derivative, and then integrate. Find an antiderivative. We'll put the plus c over the right-hand side as usual, so we'll just leave it like that. What about the integral right there? Is that real easy? Well, that's not so bad. We can do a substitution. To help us do that integral, we'll let u equal 1 plus t cubed. Then du will be 3t squared dt. So really when I look at the t squared and the dt, that's really the same as 1/3 du. And this is really the same as u to the 1/3. So I'm going to be able to integrate that. Integrate u to the 1/3 times 1/3 du. I will have to add 1 to the exponent to get u to the 4/3. Divide by that new exponent of 4/3. I also have the 1/3 out in front. And then now go back and replace u with 1 plus t cubed. And also simplify the 1/3 and the 4/3 in that denominator. right? So 1/3 really divided by 4/3 is the same as 1/3 times 3/4. And that's going to be 1/4. U to the 4/3 is 1 plus t cubed to the 4/3 plus c. Now just solve for y by doing a division. Divide both sides by 1 plus t cubed to the 1/3 power. That's going to be the same as subtracting 1 from that exponent, 1/3 from that exponent to leave a 1/4 1 plus t cubed just to the first power. And then a plus c, and I'll write it as c over 1 plus t cubed to the 1/3 power. And that will be the general solution. You should make sure you take the time to check it. As usual, take the derivative. Well, I guess I have to go back to my original equation, take the derivative. Add this thing times the function. This is going to be kind of a messy calculation. When you simplify, if I've done everything correctly, you should end up with t squared at the end. And that will check that it really does work, no matter what c is. As usual, you can also use it to solve initial value problems. Let's do another example before we briefly talk about why it works. This is going to be an example that'll look relatively simple. dy dt equals t times y plus 1. If I follow that method, first get the left-hand side in differential operator form. And then the method said that mu of t, the integrating factor, is going to be e raised to an antiderivative of the factor in front of the y. In this case, that'll be then e to the negative 1/2 t squared as a possible integrating factor. Now take that integrating factor and multiply both sides of the equation by it. Like this. And just like the last time, the magic of integrating factors is the thing on the left-hand side, even though it looks complicated, is really pretty simple. It's really the derivative of the integrating factor times the unknown function y. I can write it like this. And if you don't believe me, check it. That's always a good thing to do. Don't believe your teacher. Check it out for yourself. Teachers do make mistakes. I don't think I've made any mistakes here, but you should check it out. Now integrate both sides. Just like before, this one's really simple to do. Well, what about the right-hand side? Turns out that one's impossible to do in terms of elementary functions. And if you look at your Mathematica notebooks for different sections, there are a few cases where I've written up things about how this integral is, or integrals like this, are really impossible to do in terms of elementary functions. It doesn't mean that an antiderivative of this function doesn't exist. In fact, definitely the antiderivatives do exist. You just can't write ordinary kinds of formulas that you're used to for them. So while we can sort of write a theoretical kind of formula for the solution of this equation, it's not usually enough to satisfy most people. Of course, you could use the computer to construct a particular antiderivative here and then just put an integration constant in. But I think that's good enough for us right now. It's good enough for most mathematicians to know that essentially the solution can be mathematically constructed. It exists, even if we don't bother going ahead and trying to explicitly do the integral. In this case, we really can't do it. Why does the method work? Well, recall that we're essentially starting with our differential equation looking like this. This is the form. And again, I sort of hinted at how the left-hand side here is almost like what you would get out from the product rule. Let's imagine that there is a function, mu of t, so that when I multiply both sides of this equation by mu of t, and I will put y of t in there to emphasize that y is a function of t, I really do get something that's going to end up being the derivative of the product of mu of t and y of t. Okay, I'm just pretending that there is such a function and, in a sense, kind of working backwards and hoping that I can find the function from the assumption that there is one. This is what I want to be true in this case. And based on that desire for those two things to be equal, I'm going to see if I can find out what mu would have to be. Well, so how do we go about then finding mu? Well, first step is to literally use the product rule here and see what I get. I get the first function times the derivative of the second plus the derivative of the first function, d mu dt, times the second function. And so now my problem is reduced to wanting that to be equal to this. Well, the first terms are already equal. So now we just require that the second terms be equal. Let's see. d mu dt times y of t, that's the second term down here, needs to be equal to mu of t, g of t, y of t. Cancel the y of t's. We want d mu dt to be equal to g of t times mu of t, and then writing this in the usual differential equation form, and don't put an of t there on the right-hand side for the dependent variable, I realize that this is a differential equation that I can solve for mu. In fact, I can separate variables. I can write it like this. Divide both sides by mu, multiply both sides by dt, and integrate. That becomes a natural log of the absolute value of mu. I'll get rid of the absolute values because we just want ultimately one integrating factor here. I'll exponentiate. If I exponentiate the left-hand side, the e and the natural log cancel out. So I'm left with mu equals e to the integral of g of t dt. That went by too fast. Once again, maybe pause the recording, take a minute, get a piece of scratch paper out, and verify that calculation on your own. A few minutes ago we looked at how sometimes mathematicians are satisfied with just knowing a solution exists. That reminds me of a joke. An engineer, well, there were the three grad students, an engineer, a physicist, and a mathematician who were sharing a dorm room. And they were asleep one night when all of a sudden a fire breaks out in one corner of the room. The engineer is the only one to wake up, jumps out of bed, sees the fire, runs over, fills up a bucket of water, douses the flames, goes back, fills up another bucket of water, douses the flames again. Well, the flames were already doused. douses the ashes to make sure that all the safety measures have been taken, that we really definitely have the fire out. Checks his manual, yeah, all the safety precautions have been taken. Engineer goes back to bed. A little while later, another fire breaks out in another corner of the room. The physicist is the only one to wake up. Jumps out of bed, goes over and, tries to figure out what the fire is burning and what its spectral composition is, and based on some calculations, goes over and fills up the bucket of water, 78.23% full, comes back and douses the flame precisely, so it just barely goes out, and then the physicist goes back to bed. A little while later, another fire breaks out in another corner of the room. This time, the mathematician is the only one that wakes up. Jumps out of bed, looks at the fire, looks over here and sees that there's a bucket. Goes, looks in the bucket and sees that the bucket has no holes in it. Goes over to the sink, turns on the faucet, sees that there's water that comes out of the faucet, and happily goes back to bed, knowing that there is a solution.